Hello everybody, welcome to the Dolby Theatre, which Dolby have very kindly donated us this evening. We're in 3D today. It's my pleasure to introduce Andy Farnell, author of Designing Sound, who will be presenting his lecture on procedural audio. Just one piece of admin, this is going to be passed around, the famous AES clipboard. If you could add your name and affiliation to it, I'd be most grateful. We need it for all kinds of reasons. Thank you very much, and I'll just drop my pen lid and let Andy get on with his talk.
I'll try and find it in a moment, Ben. Thanks very much indeed. Thank you, everybody. Nice to see you all. It's a great honour to have the invitation of the AES to come along and talk to you this evening about my pet subject, my interest and love, which kind of goes under this epithet, this banner of procedural audio, just to kind of put it into context, which the next set of slides will do more than a few sentences, but it's really, I prefer terms like computational audio as well. It's kind of a good way of looking at it. So just in a nutshell, it's, instead of using sound samples, it's good old-fashioned synthesis, really. But it's a new way of looking at it in the 21st century, and how a new view of synthesis applied to interacting sound objects in a virtual reality kind of takes into account a whole bunch of different things like psychology and interaction. And so what I'll do is I'm going to present two kind of chunks to this. The first big chunk is really a PDF, set of slides, just to get us sort of talking the same language. And the second part's a demo, where I've got a load of live code, all of which will be running from this little 1.3 or 4 gigahertz Asus machine. I'll have a little bit more to say about that and efficiency and so on. So there's a kind of live code demo. Let's hope that the demo gods are going to be kind to us tonight. And then we'll kind of Q&A and talk about it a little bit. So I recognise some faces here. I know that some of you are already very familiar with kind of my area of research and what I do, and indeed have been in the lectures and workshops, and we've worked together on procedural audio topics, some of us. So I apologise to those guys who kind of know. I hope there's something new and useful and interesting in the material you'll see today. Okay, so I finished these yesterday. It's actually the April the 9th. And this slide talks about the intersection of disciplines. What do we draw upon and bring to the field of procedural audio, and what's the tagline for it? So what I have here is these kind of intersecting areas of expertise, which are all involved signal processing, psychology, psychoacoustics, perception of space, of object size, kind of auditory scene analysis, much like the work of sort of McAdams and Big and these kinds of people. There's a design aesthetic to it. It's very much about producing code which is used for the purposes of arts and entertainments. And the principal target application being video games. There's a side application here of, in the future, I hope, of CGI animation. And it kind of implies a very revised way of doing sound production. We are used to post-production. We're used to the idea of sound being applied after the fact, which is generally due to the limitations of location recording. And some are sort of artistic matters. So there's a way in CGI animation, we're kind of habituated to doing sound in post, of doing sound much earlier in the creative process. So we're creating sounding objects, which we'll see soon. There's a software engineering element to this. Many of the projects in which procedural audio is targeted may be quite large scale. So producing a game, maybe 2 or 3 years, involve dozens or hundreds of people. Likewise for CGI animation. So we need structure, and we need a kind of more formal approach. And really, this is hugely influential. The rationale to procedural audio is that sound is a physical event. It has a cause out there in reality, and any sound that we hear in the world can be modelled. And it can be modelled efficiently, effectively, and it can be given a set of parameters that allow us to control it, just as we would control the sonic properties of a real object in the world. This overlaps with some other areas, things like sonic interaction design and synthesizer design, effect design, but these are the principal kind of skills. So I've got some monumental great thing here. I kind of wrote that as almost as a joke to try and see if in one sentence I could put all of the things that this pertains to. A psychoperceptually and physically informed, real-time, computationally and space-efficient sound synthesis for the general case of everyday rigid objects, fluids and forces with applications towards virtual reality for arts and entertainment. Okay, what a mouthful. I like to think of it as the next generation in game audio. But taking a more philosophical slant on it, which is kind of really underpins a lot of my work and where I'm going with it now, it's a view of sound as a process. And I'm going to unpack that a little bit more in a moment. Another way of talking about it might be a reasoned approach to sound design. Why reasoned and what's so good about reason? Many approaches to sound design are ad hoc, they're experimental, not in a bad way, that's good. The way that can be bad is when you've created something and you lose your place, you lose your mark, and the next day you go back and you don't know how to recreate what you did because you haven't got a sort of internal working model of the process that you went through to get there. So a reasoned approach to sound design, maybe another way of talking about it. Okay, so once upon a time, games had this strange way of doing things. Does anyone remember Myst? Myst presented a series of photographs that kind of dissolved between the scenes, and it was written up as like the most immersive game ever made. Its principal description was it's immersive. And these worlds weren't photorealistic. They weren't photographs. They were artistically drawn in a kind of equivalent of Photoshop, then I guess. Very interesting because they were photographs essentially. They were static images. Around about the same time, about the 90s, another technology was competing with this, and I like to imagine. Kind of like sliding doors or what is it, alternative universe realities. What would have happened at a meeting where a games company were commissioning ID and Myst to make a new title, and ID turned up. If you know Wolfenstein and the early, these were the predecessors, the prototypes of what is now virtually every game. An immersive 3D virtual reality with rendered objects, lighting, and it was very, very embryonic at the time, but it looked awful. Aesthetically, it just sucked. So they were being compared to the guys from Myst, and what would have happened if the people then had said, you know, this 3D interactive stuff, I mean, it's great in principle, you know, but it'll never fly. You know, so we're going to stick with the dissolving between the static photographs. Well, that didn't happen. What happened is, well, we know the story of gaming and what it's become now. But that's what happened to audio. Audio got stuck in the early 1990s and stayed there for almost, well, you know, a decade. Many people that I talked to around about 2004, I said, maybe this sounds a little bit kind of dismissive or a bit rude, but you know, I kind of think that game audio is stuck 10 years behind where it should be. And they said, no, you're wrong. It's stuck 15 years behind where it should be. You know, it's much worse than that. So it really motivated me to become involved in moving things forward from having sound samples, which I consider sound photographs. Although sound samples sound is a function of time, and so they're actually slices of functions of time, they still don't change in time. If I make a recording and I go back to that recording later, it still has the same properties as it did when I recorded it. Interactivity, therefore, is a question of, within that framework, is layering and selecting between sound samples. Okay. we maybe won't unpack this today. It's to do with degrees of freedom and a phenomenon that's going on now. Holly Webb is that media being a push there are forces trying to make media be a push technology. You can see a lot of evidence of it: asymmetrical download and upload, and a tendency towards. But it's about delivering artistic vision, which is how a film is. You know, a film begins with a director's view and a script, and that's delivered to the end point, and it doesn't change. Whereas a game is kind of flips it all around. The game, the user, the player becomes the controller of the game, and there's a counterforce towards that. So, okay, why would, other than the aesthetic reasons, why might we want to do procedural audio? What advantages would a computational approach take over using sound samples? And there are some very good cases we can make from a computer science point of view towards dynamic audio being of use in the future. Here's one of them. If I assume that the sound is caused by interactivity between objects in the world. So if I have two objects and I bang them together, and collision is my mode of interaction. What I have there is one possible sound between two objects. If I bring three objects into the world, I have three possible single interactions between them. But interestingly, what happens when I bring four in? The interactions are the edges of a fully connected graph. So I have six possible interactions. And what I end up with is a polynomial growth of the assets that I need to populate my world. So as I add more and more assets to these hugely growing virtual realities that occur now, I have to send my location sound recordist out to record all the possible interactions of all the possible things that could happen in that world. Now, what if I could model that and begin to get behaviours for free? So I just model some of the interactions, and it turns out that as long as my rule set is consistent and includes all the correct stick-slip friction and impact and various physical interaction models, I can get unexpected behaviours that I've never actually tested before. And so what we're able to do is, instead of having n squared growth, we can bring that back to a linear or better growth. Okay. An example of this kind of going wrong, in my opinion, was Heavenly Sword. That was a game that shipped with, I think it was around about 10 gigabytes of assets. And what that demonstrates to us is that and there are many reasons for that. It had a full orchestral score recorded by, I think, the Prague Philharmonic. It had multiple dialogues recorded in multiple languages, choices of regions and so on. But still, it was a huge bloat of assets. And what that meant is that because it was on multiple DVDs, we're effectively no longer in a random access world. We can no longer just dip into anything can happen that we want in the interactive virtual reality, that we're moving back towards a linear narrative. And the reason is to do with the way that the data is brought from secondary storage into what's a very small buffer on the game's consoles. And so it has to be presented in such a staged, semi-linear way that it's almost like a kind of film. It's a game, ostensibly, but it's a film because of the huge amount of data and how it has to be presented. So that marked interesting area. Okay, so just to say a little bit more about that, data throughput's an interesting problem on the modern consoles. When we look at the way things are growing, we're seeing a massive increase in CPU cores. If we can leverage the parallelism available there, then using CPUs is fantastic. But if we've got a data-driven model, we're up against a hard limit. Even with a 64 physical connected 64, it's going to be a long time before we jump to 128 data bus. It may never happen. We may go optical before then. So what's happening in terms of data congestion if we're trying to meet the demands of this kind of growth in audio is a problem already. So we do it at runtime. And the concept that we're bringing to this is the concept of deferred form. We'll do it later. And doing it later isn't a greedy optimization. Doing it later is a wise choice, because it's only at runtime in the context of when the player is actually doing something that we really know what we want to do. A lot of game audio, unlike a film, which is being, when you're doing post-production, the visual content is cast in stone, it's fixed. It's not going to change. Very unlikely the director's going to run down to the sound room and say, I've decided to cut that 5 minutes and replace it with this. But when your game goes out, you have no idea what the exact visual scenario is going to be when the sound is played. So it's a contingency-based philosophy. We want to say, well, these are the kind of things that might happen. These are the possible forces that might interact with my objects. These are the way they might kind of come together and so on. So it's point of delivery, interactive, and crucially, we trade off CPU for data space, which makes sense given the current developments in computing hardware. Okay. So it's just synthesis, right? It's just synthesis, but let me give some caveats to that. Why go along this whole procedural computational audio thing if it's just synthesis? Well, for one thing, synthesis accrued a really bad reputation in the 1980s. People, just from a marketing point of view, people think of synthesis, they think cheap, they think synthetic food, they think something somehow low quality. This slide contradicts itself. Phil Oakey there is kind of lacking the big hair, but I just thought that shot really typified what people think of when you say synthesizer. And of course, it's driven by the music technology industry. Now, that's great. I've been involved in that industry for a long, long time, but it's about cultures. It accrues certain attitudes and certain points of view. Ostensibly, most of the DSP work done in the world is done in music departments and music technology departments. It has a musical slant. It's not aimed at the general case of sound synthesis, and it's not necessarily aimed at sound synthesis which is done in a virtual reality context. Also, synthesis has accrued, I've put a legacy of poorly understood methods, maybe that's a bit uncharitable, but they've been used as is technologies, so FM is what we associate with Yamaha, rather than kind of thinking of Chowning's mathematical basis for FM and its interrelationship with Wessel's, Beauchamp's work on wave shaping, and that it can be shown that they're equivalent, and there's a continuum of methods, some of which are complete and are able to synthesize all possible sounds, some of which are very hard to parameterize, some of which are very, very easy, and so on. So perhaps we can take a more mature view of synthesis with 2 decades of its use behind us. So yeah, this is the general case is what I kind of want to push here. The Italian school, that's Rochesco's. There was a big study done in Italy, in Padua, Verona, Ferrara, this kind of group, which was kind of based around the idea of the sounding object. I've no idea why that's gone. Can you? There's something going on there. So the sounding object is an idea that. Oh no, it's still there. Okay, it's there on mine. It's just not that. Okay. So a sounding object is, unlike Pierre Schaeffer's definition of a sounding object, which is a compositional device, a sounding object is just any object in the real world, which if we could kind of model it, we'd model its sound producing aspects. So, here's a sounding object. It's a vessel containing fluid. We can shake it. It makes a sound. It has a impact method. It has a different impact method, which depends on where we hit it and with what we hit it. And we can reduce it actually to a fairly small set of methods, which we can explore and apply to each of these sounding objects. Sounding objects, generally we consider the interaction of the player with the object, but we also consider object-object interaction. So if I drop A onto B and it rolls, or I take C and I collide it with D or something. And objects can have internally referential behavior, such as fragmentation. So if I take an object and I smash it, it becomes 3 separate objects, say, but there'll be a physical relationship preserved there, such as the mass and area of all of the for a plane. will be the sum of the original. The sum will be the original object, and so on. So this can help us calculate the modes of vibration and such like. Another upshot of looking at this is to devise a taxonomy of objects, which has been done in the past, but I kind of wanted to try and develop one that was more appropriate for the computing aspect of it. So there are certain classes of sounds, such as high energy sounds, thunder, explosions, things which disobey the normal laws of acoustic propagation. We might like to put those into a separate class. We might like to pick idiophonics is an interesting class. They're just struck rigid bodies. They have no sort of attendant components to them. So we can use modal synthesis to approach these and so on. Okay. So is this just physical modelling? Isn't this just physical modelling? Yeah, it's that too. Physical modelling. Yeah, it's something that's involved. But it's not exclusively physical modelling. This term, I think, physically informed modelling comes from Perry Cook, who's one of the founders in this area. Perry Cook, if you like, is one of the grandfathers of computational audio. His book, Interactive Real Sound Synthesis for Interactive Applications, was a landmark in this field. And he talks about simplifying the physics, physically contextualized modeling. Why make that distinction? Because if we allow the concept of physical modeling, we go too far. Using finite elements, systems, waveguides, or many of the ways that are used to do actual physical modeling, where we're looking at the particle or molecular level interaction of forces, the problem just explodes. What we discover is that we can make massive simplifications and just use certain physical equations to drive what we might call parametric models, like AM, FM, wave shaping, wavetable synthesis, granular synthesis, or the various methods. So we get the computationally efficient production method, but we still involve modelling of physical process. It's just not exclusively done using that method. So there's a hybridization of methods in this. Another important thing to say is that it's the aim is to make it extraordinarily compact, and we can. I was heavily influenced by the demo scene, which is kind of games hackers whose prowess is in producing pieces of code which are fully working games or fully working little demos of graphics and sound, which are basically derived from equations. They're extraordinarily compact. You can have an entire game in 1K of code with sounds and graphics and so on. So it's a kind of like an obfuscated C contest or something to produce this. This really kind of got me thinking. You don't need very heavy, very detailed models. You can do things with very little code. And at the time, all I had was a 500 megahertz machine. So I decided, instead of just kind of getting all upset about that and thinking, hey, I don't have the resources to do this kind of research, I thought, well, if you've got 1 gigahertz on a console and you're prepared to give half of that over to sound, can I produce a full demo of all the sounds needed for a first-person shooter game using just analyzing physical processes and using classic synthetic methods? And the answer was yes, I can. And I did that in 2005, and I took it round to lots and lots of games companies and showed them, and they just laughed. They said, "This can get it," and I was absolutely shocked. Now, I'd really like to unpack that some more, because I think this is to do with attitudes to technology and what we might call persistent mythologies. There was a persistent mythology around that this is something we can't do. If you say something for long enough, you talk yourself into believing it's the truth. And for like almost 15 years, people would say, yes, we'd really love to do computational sound, but you know, the CPU just isn't available. suddenly the CPU became available and nobody noticed, and it happened around about 2005. Okay, so the other reason for saying this is not just physical modelling and not just synthesis is that in doing this, what I discovered is that there was much more territory underneath and above and beyond the whole project, which was really to create frameworks for doing this reliably in order to create workflows and create candidate tools and ways of approaching this. So I don't think there's too much to say about that. One of the key concepts is a layered approach. So much like the sort of OSI model is for networking, layered models are everywhere in life. They're all about abstraction, and they're all about making things so that we can take layers out and replace them with other things which are equivalent. So what we get from a layered model of computational design for sound is abstraction, the portability, being able to take it and put it onto other devices easily. And one of the proofs of this, a proof of concept, was done by Dan Stoll, who's now at Queen Mary University, who basically took all of the content of the textbook I wrote on this, Designing Sound, and re-implemented a lot of the examples in Super Collider, showing that the implementation layer could just be changed arbitrarily to a new implementation layer, and everything worked and sounded fantastic. Quick look at the layered model. So at the topmost level, we've got our behaviour. What I'll do is I'll give you an example which maybe brings this alive. A bouncing ball. We can describe the behaviour as that, well, there's an object and there's a release event, and then some delay time later, the ball hits the ground and makes a bonk sound, and then it bounces up. It loses some of its initial energy and goes down, bomb, 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 something like that. Doesn't really say much about what's going on. To understand that, we need to hypothesize a model. So model is, well, we have a potential energy, it's converted to kinetic energy. So S equals ut plus a half at squared, and we get mv squared kinetic energy, and we lose that on the impact, and some of it becomes sound, and some of it's stored as elastic energy, some of it's released back in the bounce, and so on. So that gives us a model, but that hasn't said anything yet about how we might go about turning this into a signal from an observer's point of view of its displacement of the air. So what we then do is we apply a method to this. Now, methods really are the synthesis methods. They may involve analysing the points on the surface of a membrane. They may be finite element. They may involve understanding the Riemann modes of a sphere. They may involve Green's equation for the propagation, but ultimately we're going to use FM, AM, granular synthesis, a common method to implement the production of the sound. And finally, once we've got that, we need a way of actually implementing it. We may do this in C++, we may do it in Pure Data, Super Collider, C Sound. We've got lots and lots of tools which allow us to turn things which are available at the level of the method into an actual bunch of code that we can get running on a processor and making these sounds. So with this, we're able to pull out any layer of the stack and replace it with an alternative. So we may replace our method with an additive approach, or we may come up with a more efficient model which bypasses some of the physics in the initial analysis. So, yeah, it allows us to use different stuff. And now this is about the design, not the structure yet. The structure is something we could talk about more to do with the MPEG, the structured audio SAL 04, which kind of died, I think, really. Okay, and a side effect of this is flexibility. So we can have classes of models. They don't necessarily have to do one thing. A class of model might be a cylinder closed at both ends, which could be a tin can, could be a Coke can. We could make a great Coke can model. But we could scale that perhaps and make a big oil drum. Yeah? Or we could use a vocal track model and find it's great for making human speech, but it's also great for making monsters, and it can be subverted to make various mammals or bird sounds or something like that. So we tend to find that there are base models from which we can derive more specialized subclasses. That makes them user customizable. We can envisage some sense in which there are people who produce procedural models at a high level that they can then be used by sound designers closer to the production. This is where the software engineering aspects come in. To what extent do we want to reuse pieces of code? What we discover is that there are certain, I call them signature processes. They're very light, similar to the flexibility issue. There are certain things which, once we've done them, we can just reuse that piece of code in lots and lots of contexts. So, for instance, a stick-slip friction model that might be used to make a squeaky door can be used to make the sound of a leather seat, can be used to make the sound of a sponge on a window. Can be used for sort of all kinds of different things that need that model. And what we find is that there are various specialists in these areas that have made very compact models, like Stefania Sefrain has worked exclusively on contact models, like Stickslip. So we can use a lot of her work for that application. Okay, another fantastic side effect of doing this is summed up in Father Ted when he says, "No, Dougal, this is very, very small. That's very, very far away." And if we didn't have binocular vision, we probably wouldn't be able to do this so well. But it's an interesting fact in computer graphics that we have variable costs to producing assets. So it's called MIP mapping. If you've got something that's very, very far away, you simply render it in less detail. You use like an 8-bit representation with 16 pixels instead of like a 24-bit with high resolution. Well, we don't with sound samples we can't do that. If I have 10 sounds in my scene, the cost per playback of sound samples is exactly the same as if I have 128 sounds in my sound scene. Some of them may be very distant and hardly contribute anything to the total mix, but their playback cost, the computational cost, is exactly the same. What procedural audio approach gives us, a computational audio approach, is level of audio detail, load, L-O-A-D. Level of audio detail gives us elasticity in the sound production, so that the contributions of sounds which are in the periphery or very far away or maybe not particularly relevant to the context, we can obtain focus in a bizarre kind of way. Different kind of mixing, psychoacoustic mixing, in which the focus of the player in a real-time context determines the level of audio detail in which the parts are rendered. There's been some work done on this at SIGGRAPH. I forget the authors at the moment. Obviously, there's an interesting relationship between this and perceptual compression. Temporal masking, in-band masking, and so on. But we're adding more psychoacoustic attributes to this decision making about level of audio detail. Okay. Just a quick cap of some historical work. These are some of the great figures. Julia Smith, Perry Cook, Denise Pay, Van Dundel, and the current work that's going on. I don't know if any of you have seen Stefan Bilbao's amazing book on numerical sound synthesis, which is a treasure trove of stuff to be unpacked. Dylan Menzies doing a lot of work on procedural audio in gaming and so on. So it's becoming a fairly active topic now. When I first started doing this in 2004, 2005, I couldn't find anything. And it was actually kind of accidental that procedural audio became the working project title for that. There were some commercial stirrings now. LucasArts are doing some work on fragmentation models that they're using in some games. I don't know anything about that, and if I did, I wouldn't be able to tell you. Audio Gaming are a company based in the south of France, a guy called Amaury, who's decided that he's going to build a middleware engine. It's procedural audio. He described it at ERCAM when I met him as, some people get a film made of their book. Mine is the company of your book. Which was a very nice thing to hear, that they've managed to kind of really start to commercialise this work directly. Okay, there's a lot of resistance to it still, though. I still encounter resistance. I want to go back to that statement I made about, oh, there's not enough CPU to do it. The mythology of the exponential function. We as human beings are very, very, very bad at understanding the exponential function. We just don't get it. Yeah. One of the problems with it is that you zoom in. You often hear people talk about the knee of the exponential function when we get round the corner, but you never do, because the more you zoom in on it, there's the exponential function again. Zooming in on it, and the context you're in always looks like the one that you came from. So it always looks like the good stuff's just around the corner, or the bad stuff. This mythology, I think, is kind of what was behind a lot of people not investing in computational audio. I also recognise that the commercial world of games, it's about shipping titles, and are often very conservative. It's actually one of the more conservative industries, even though we often think of games as being highly progressive, and not much investment, as far as I can see, into really trying out these new technologies. For a long time there's been a reluctance to do so. I think there's some movement now. So we've had huge CPU growth. We're able to do it. The new objection, but I think this is a straw man too, there's knockdown arguments against this, is the question of realism. People always say, well, you synthesized it, the realism just isn't there. In my experience in entertainment, people don't want realism. They hate realism. Realism is always really disappointing. We want hyper-realism. We want, the sound of a gunshot is never just a gunshot. It's somebody banging a dustbin layered with, Lord knows what, to make it huge and hyper-real. So the realism arguments, it always seems very poor to me. And I don't know of many good psych studies, A/B tests using high-quality computational audio, the kind of things that the fluids that Zeng and James are doing at Cornell against actual sounds of fluid. I think that you could not get correlations above chance. I think most people would not know the difference, average audience. Yeah, it's that good now. Yeah. So the cost of production, this is a good argument against it. I think the economic argument against it's still very strong. I can't just turn around my entire tool chain. I've got skills invested in doing things in a particular way. I've got equipment invested in doing things in a particular way. So I think what the future ultimately, let's come back to that. What the future's going to bring is, I've always seen that it's going to be an incremental movement along the road from data-based data models of audio to fully computational audio. It will be introduced alongside, and there are certain areas where it will never replace it. For instance, human voice artists aren't in danger of being replaced by speech synthesis very soon, I don't think. Leveraging GPUs, a lot of this is parallelizable. It can be fitted into a model. Sound is actually great. We have a gift, a real gift, that there's this glut of CPU available in the form of GPU cores, and we've done almost nothing to really use that for sound synthesis. I've seen some amazing demos recently of sound at Queen Mary done using the CUDA programming toolkit to bring some waveguide type models into the GPU, and boy do they sound good. It's just unbelievable. So we can do this for the general case. We can start using the GPU cores for our game audio, for our collisions and cars and things like that. So I'm guessing that a lot of it will initially be proprietary, but it's in my nature, in my philosophical lifestyle. I'm an open systems guy. I'm into open source, and I really believe in standards. I think standards are what makes everything work. So I'm kind of hoping that what emerges from this is ways to produce, to codify the production methods for procedural audio in the next couple of decades, and have an open basis for that, so that they can be interoperable and so on. And another thing that we're still missing, I call it the Tron moment. Some of you here will be old enough to remember that once upon a time people laughed at computer graphics, and directors would say, you will never have computer graphics in films. The last 4 or 5 films that I went to see with my little nephews and nieces were all entirely CGI animation. Yeah. What changed it? Well, oddly enough, there wasn't actually very much computer graphics in it. So the irony is Tron, but the film Tron basically said, computer graphics, we're here, this works. You can have an entire film which is done in CGI animation, in computer graphics world. And people loved it. And after that, you can see that the whole, the story of CGI replacing drawn animation, and how it eventually became more cost effective than the drawn animation and so on. That's going to happen with sound. I really believe that's going to happen with sound. How and when is still a tale to be told. I spend a lot of time advocating this stuff. Since I wrote Designing Sound, my work really has been lecture tours, showing people demonstrations, talking about it and advocating it to games companies, and educating others in the ways of procedural audio. So just nip back to that rather pretty slide here. The reason I chose this was to do with people expecting perfection in the model. And that perfect becomes the enemy of the good. And I think there's a reluctance to jump into this because we've already reached such a high bar in terms of the audio that is produced for games. And we would basically have an entire studio at runtime there, but it's using a data-driven model and sound samples and so on, that to revise that, almost certainly what you produce is going to be substandard compared to what we've got. So we've got, against this very high bar, there's a risk-averse culture towards this sort of development. And so, yeah, perfect's the enemy of the good. I think that sums it up quite well. We can do good enough. So what I'd like to do now is to quit with the PDF and run through some sound examples. These are the kind of things I work with my students. We develop procedural audio thinking. We learn how to analyze and attack a particular sounding object, decompose it, reconstruct it in DSP, and work out how it's going to be interacted with. So I think we can just leave that, come back here, and if the sound is uncomfortable for anybody, please raise your hand. If you can't hear it, I can push it about, I think I've got 4 or 6 dBs of headroom on this knob here, not much. Okay, I'm going to go through these very quickly. How long, time check? Anybody?
You've got plenty of time.
Okay, maybe we'll find some ones that are fun. Okay, I'm sure. Okay, I hope nobody will get bored. I'll try and read that. These are simple materials. They're done with filters. And the reason for this particular demonstration is to show how incredibly simple some models can be. Here's a range of materials from China, okay, and what's making these sounds is these 4 bandpass filters. They're being excited by a noise pulse, and the center frequencies and Q factors for the bandpass filters have been chosen just by looking at hitting some materials and looking at them in a spectrograph. Yeah. So if I want, I can use these filters as a modal operation to drive other sound signals through. We'll see some things of that a bit later. Okay. Here's a classic additive synthesis model. It's a telephone bell. Sounds like this. Okay, so the analysis of a sound like this is done very simply by breaking it down additively, and I'll mute one of the bells because there's 2. You can see, oops, what does one of these things actually look like? Oops. There's one of them. And, oh yeah, that's what we're looking at. If anyone remembers taking one of these sort of things apart when they were younger, it's a kind of literally 2 little bells, and there's a hammer that bangs backwards and forwards between them, driven by an electromagnet that kind of pivots. And here's one of the bells. We can start taking out some of the partial groups until we're just left with the beta hitting the surface and then the rattling of the electromagnet. And all of this is inside a housing, and the housing is just made to model a very simple modal container with a sort of, the plastic's called Bakelite. It's actually very reflective. It's more like the properties of wood than the plastic. So we'll bring back in some of the vibrational modes and then bring back the other bell. Okay, not very interesting in terms of synthesis. This is old stuff. So like this is the classic example. Here we have St. Peter's Italian church bell. This is made from this spectrum. So we look at the spectrum, we translate these into ratios of the fundamental. But then we can do things like dampen the bell. So we'll throw a huge blanket over it. We can move its pitch around, we can make it and so on, to scale the partials. And there's only 10 in there, don't need much. Additive synthesis is very, very good method for sparse spectra. You know? And this is, not only is it sparse, but they're fixed. So rigid bodies with sparse spectra, loves additive synthesis, and it's very, very cheap to do. We can literally, on a modern CPU, we can have hundreds or thousands of these things running. Okay. Here's a slightly more interesting model. This is an edge-supported laminar, a glass, aka a glass window. It has some dispersive effects at the edges where it's supported. So what we're using here is a mixture of noise and ring modulation to shift the shift the spectrum as it interacts with the edges and bleed them away from their spectral original position. So we can change the size of it and the thickness and so on. Okay. It's just modelling the material properties of glass, the speed of sound in that material, and the geometric representation. So you see there's two factors here: the material properties and the geometry come into effect in these basic idiophonic modal models. Let's increase the complexity for a moment. Often what we find is that the actual parts of a sound themselves are very simple, but it's the way in which they're activated which makes the sound recognizable. So here's just a little tiny sound. Oh, that's interesting. I lost one of my sounds, I think. There he is. Okay. So we have this little, it's just a click. The hum's not supposed to be there. Okay. But as you move the ratchet, you're projecting the cosine. So you're moving in a straight line, you're tangential to the circle around which this thing's moving. Here's the pattern that we get. Okay? It's just that sound, but what gives it its characteristics is macro behaviour. Okay, so we're going to see more examples of that kind of thing. Here's a more complex version. Stickslip friction model can be very easily stated in that the intensity of an impulse is directly proportional to the time since the last impulse. Now we know this from earthquakes, from plate tectonics and stuff. This is why it's really bad if there hasn't been an earthquake for a long time, because you're going to get a big one. But there's been one recently, you're going to get small ones. So what we have here is an acoustic signature process, which our brains immediately recognise as a stick-slip friction situation. I'm feeding this into a wood-type modal filter, like the ones you saw with the bandpass, and then a waveguide which imbues it with the characteristics of being a square. So it's got squareness, it's got woodiness, it's got stick-slip frictioniness, and it goes. Okay. So think about how that would actually go. What would this implications be in a game? You go to open a door. Normally, you would have to synchronize the sound sample with the opening of the door, which would mean that the door would have to either open at one speed, or if you were able to speed up and slow down the sample, you'd change the pitch of the door. of the whole sound. But of course, what we're doing here is we're just being able to interpolate between any two positions, the closed position, so we could open the door as slowly as we like, and we could even make the rotational velocity have an impact on some of the finer nuances of the stick-slip friction model. So we have this ratio of dynamic to static, which will say you can try and be really quiet and open the door very slowly, and it will squeak in a different way. So move to something more interactive based on the macro level behavior. Okay. Let's look at the footsteps then for a moment. Footsteps, these are based on what we call the GRF, the ground response force of a walking biped. We don't just have clip, clop, clip, clop, clip, clop, clip, clop. What we have is these three phases of the foot, which are overlaid on each other: heel, outstep, ball, and 2 feet, which behave in different ways depending on whether you're running or walking. So this is a kind of the analytic version of Foley. And if you study what Foley artists do, they really understand the movement of a character. We're able to create models where what I'm doing here is using these 3 overlapping polynomials. So we got the separate control over each of the parts. Yeah. And then we can dilate or compress that GRF function to give us different kinds of behaviors. Okay. What we then discover is that there are nuances to that which depend on the movement of the actor. So if you're running, if you're accelerating away, you're doing lots of work on the ball of the foot, whereas if you're slowing down, you're doing negative work on the heel. So the ratio of these shifts, what we can do is we can just take one variable being the actor speed and derive the other parameters from that, so that we get, as we speed up and slow down, we get a kind of automatic differential behavior. Kind of thing, yeah. Come on. Okay. This is an even more complex model in terms of the interaction of macro level parameters. I'll just tell you what it is before I run it. It's a squeaking wheel. So if you try to over accelerate, the wheel loses traction and begins to skid. But then, of course, it heats up. And as it heats up, it becomes more plastic, it adheres to the road better. So we've got these counteracting forces in the model, a macro level behavior. What also happens is the engine will over rev because in the transmission there's nothing for it to bite onto on the road. So we've got a really interesting interaction between the engine speed, the point at which the slip happens, and the consequent sound. So this is not a very good sounding model, but it demonstrates the interaction of the parameters. So I've got a kind of silly little game thing here where there we go. And when I'm just trucking along, if I suddenly try to accelerate too quickly, if I go slowly, no worries, but if I go too quickly, and you can hear the stick-slip model kick in. I need to. I've got a funny feeling that I've got left something else running. Oh, well, never mind. Right, the next series of slides show this software engineering aspect, that we can start with small pieces and we can build these small pieces into larger chunks, and then we can reuse these larger chunks and signatures to produce larger things and larger things. And what we discover is that many of the objects in our ordinary everyday experience are composite mechanisms made up of, can be broken down into things that we understand much better, and when we combine these together we get more complex sounds. So here's a really typical example of a little switch. Okay. The switch is just designed to emulate a plastic panel. A switch is actually quite complex. You've got poles and things, throws, things that will impact, but it's just an impulse into a plastic panel. And that's reflected in the design, which is extraordinarily simple. There's a line envelope there, some noise, and a bandpass filter. Okay. Now, using this idea of the poles and the impact pattern, we can build more complex switches, and we can involve the panel on which they sit. So, and we've got these guys here, you know, we can switch these along. And when we look inside, we discover that the design of it has this little ping, you know, these very subtly different slides, and we combine them together in a macro. So we've almost got like a switch kit here. We could make a whole bunch of these guys, and we can increase the complexity of it to make something that's got a whole load of things that happen when you move it. Okay, and eventually we say to ourselves, hold on, this is and this approach, this is Microsound, this is Curtis Rhodes' field, is construction of complex sounds in the time and in the time frequency domain, but particularly in the time domain, where we start with what are essentially almost indistinguishable clicks, and we combine them together in time patterns to produce things which are recognizable. I'll just give you a little run through this. So this is a game, and it's fairly obvious what you have to do. I'm under real pressure here. Easy one. Okay. Oh no! Oh! Oh, it's getting tense. Oh! I hesitated. We're showing off. Okay. So, right, what's inside? Let's get down to the nitty gritty. Obviously, there's some game logic. It's a silly little game. You could put this on a pad or a phone or something like that. But there's clearly the game is very sound based, and what we call the ticking clock in you know, you guys know, it's a tension bed. In any other kind of scenario, we'd say that's a tension bed, and it's there, this tick tock, tick. You know, it's kind of like, so how do we model this clock? Well, I could get a loop of but maybe I want to do more things with it. So here's the kind of way that I'm going to unpack this. I'm going to say, you know what? Let's see if we can just get it running. I have to do a little bit of editing on the code here, perhaps. Maybe there. Maybe I need to. Oh man, I'm running some. There we go. Serious CPU. Find out that it's made up of these parts, you know, and we can break them down. How did I work these out? I had a very high sample rate. The first time I ever worked at a very high sample rate, and I had a contact microphone, a piezo, and I put it onto a little tiny watch and recorded it, and then slowed it down 50, 20, 30, 40 times. And what I was amazed to hear was that when people say as regular as clockwork, clockwork is about everything being in precisely the right place. And what you hear is this store of energy in the spring releasing that through the escapement mechanism, digga, 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 and then suddenly a cog goes round here. And as it goes, ching, and the next one goes, boom, and the hand just goes, and then the whole thing happens again. I was like, wow, it always does exactly the same thing. You know? So let's kind of analyze the interconnectivity of these physical components and realize that this intricate little ticking sound is just, we can sequence that, you know, with small time domain microsounds. So if we look inside the TOC object, we'll see, what is a TOC? A TOC is a bunch of these things being sequenced in a very fast time. If I get rid of some of them, there's one. But that itself is a microsound. These are the vibrations, these are the reflections around a circular, center-supported metal disc, aka a cog. And that gives us the microsound, if you like, the atomic microsound. And then I'm going to put a bunch of these guys into time. You hear that? How we're building that up there? and then we're going to have 2 of those, one on a slightly on the opposite phase, and then we'll put our escapement mechanism in. It's very subtle, yeah, okay. But what we can do is we could change the timing of this. We could and we could change the size of it, because there's what we can do is remove the body from the clock. And I actually did this when I was about 5. I had a big Mickey Mouse clock like that. When you take it apart, sounds like that. Okay, we're taking the body away. So here's the plastic body, which we can put back in. And if I want, maybe I can enlarge that, just scale the whole body here. Oops. And in theory, we could scale something down to a little watch or a big grandfather clock and change the acoustic properties to make it sound more wooden or something like that. So we got a class of model, you know, and we can, so, okay. See how we're building complexity from smaller things to bigger things. Here's another example of an electric motor. I won't say too much about how an electric motor works. You have a rotor, you have a stator, you have some brushes that touch it and they make a click, click, click sound, and that's within a resonant cavity. But what really gives the motor its sound is its macro level behaviour. Because when you apply a current to a motor, it's initially still, and it means that the theoretical current flow is infinite. Yeah, so its acceleration, its angular acceleration at the moment you apply it is vertical. It speeds up very quickly, but as it approaches its maximum theoretical speed, it's asymptotic to its top speed. So no matter how much more energy we put into it, it sort of never gets there. So we get this particular shape. When we switch the motor off, the decay is linear because the loss is only to friction, as near as we want to say. So, and then when the decay comes, it has a different shape. So we'll recognise this when we speed it right up. It has the macro level behaviour of a motor. We can get more detail into the stator sounds and so on if we want. What we can then do is we can take a bunch of these and say anything we can make, we can instantiate as many of them as we want. So he's just that same motor object instantiated many times. Okay. Now what I'm going to do is I'm going to show you another model. This is a very simplified version of it. It's a fan. When a fan rotates, the blade is effectively pushing a pulse of air towards you. So we can model this as it's usually sort of like a Gaussian pulse of air. There's a very efficient closed form for doing this. It's 1 over 1 plus k cos x squared, where k is the function which gives us the width of the pulse. So we can just get one of these, gives us a nice little purring sound. There's our pulse width. Yeah. This is when we're in the axis. We are in the perpendicular to the axis of rotation of the fan. But as a fan blade moves around, it has what's called an edge noise. So if you imagine kind of being in the axis of rotation now, if you were to follow it round with a microphone, you'd hear it just hissing. But of course, as it comes towards you, it's going shoo, shoo, shoo. There's some Doppler. At this point, it's come towards you. At this point, it's receding. And it's also being modulated by the other pulse. So this next model brings the edge noise with the displacement noise into the fan model. Again, we can narrow the pulse width. Yeah? And by mixing these two, we can create the effect of moving the fan around in space, so we're on axis or perpendicular to the axis. Computationally very efficient model. So what we're going to do now is we're going to combine the fan, the electric motor, and an acoustic space model. And let me just contextualize this. I apologize to my students who know the routine. So you're being chased by zombies, and they've cornered you in a room, and they're screaming brains, 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 and there's no way out. Okay, but there's always one way out. Yeah, you look around, and there's an air vent on the wall. So you grab the crowbar and you smash the air vent, and you climb through it, and you can hear them coming, brains, brains. But there's a fan in your way. Yeah, and you're in this acoustic space. Who's played Half-Life? Okay, so you know what I'm talking about, right? And you can hear them coming, but you've got to shut the fan down somehow, right? This is the scenario. So Valve did a brilliant job, by the way, of making that, even in the very first one, of making the space be an acoustically viable space that you could actually walk into and then hear the other sounds through. But in this case, we're going to procedurally produce the entire aircon model, which is here. And I'm going to just push a couple of dBs here just to give you some of the detail in this model. If we look at the arrangement, it should actually be fairly straightforward to understand, even though that's a big old model. Here's our motor. Here's the rotor and the stator, and look, they have a common phaser driving them because the fan is on the same shaft as the motor. They're physically linked together. They're going through, down here you can see waveguide based, very simple waveguide based acoustic model. But listen to the way that the parts work together in this when I shut the system down or power it up. Reactivate it. Hear how the fan will hit a sudden resonant mode of the acoustic system. So as we start to produce composite procedural models which involve simple but connected components, we're able to produce much more complex and interesting behaviours in the games world, even though the individual sounds themselves that constitute the model are fairly unimpressive. We start to get emergent behaviour, and this is the key to this demonstration here. Okay. This next one shows you the potential for this kind of interaction at a large scale, and how we start to get very interesting big behaviours for free out of procedural audio. So this is showing the systematic version of it rather than the individual models now. Here's a windy day. Oh, interesting. I think I'm missing some things in this. Yeah, I've no idea why. Anyway, can't see by looking at it. Okay, well, what we've got here is a bunch of when you hear the wind, it's not the sound of the wind, it's the sound of the things that the wind interacts with. So it's the turbulence around those objects as the wind speed rises and falls. And what I'd like to do is, to create an immersive sound environment, is we have it so that there's a kind of an apparent wind, but the individual objects in the scene that we navigate each emit sounds, and they're spatialized within the virtual reality. That means that I should be able to add and subtract new things from the wind scene. I'm a little bit mystified why that one's not playing out so well, but you remember. Okay, here's some rain. I know what it was. It's the gate. Yeah, I said don't worry about the gate, but when it was dipping down there, the gate was snapping it. Okay. Okay. This is a windy day, a rainy day. There's Green's function-based impacts of rain. There's water. There's thunder and lightning. It's all very cartoon. But bear in mind, this entire model was synthesized and is being synthesized now on this little laptop. Was originally done on a 500 megahertz machine. got to approach this with highly efficient methods. And the rain effectively produces a particle system. This is a granular It's a granular technique where we basically allow an impulse to excite a short filter and allow it to ring at a particular frequency. So, okay. Now you remember the window. This one. Yeah. Using AM type methods and a square laminar model. What I would like to be able to do is to be sitting inside on a windy, rainy day and place myself close to the glass window such that the wind speed now influences the particle system, which represents the rain, but instead of driving it against a ground object or something, the impulse response that I'm going to use to convolve my rain signature with is the window. So this is sitting inside on the same windy, rainy day. Okay, here's the glass window. And you can hear that when the wind speeds up, that noise signature is getting the characteristics of the window. Yeah? I think it needs to be a bit more resonant, but you get the idea. So what we can do is produce objects, place them into our procedural world and have them become part of it based on what's happening there. Okay, I've just got a few more to go through and then we'll do Q&A. This is the reuse of the vocal track model I spoke about. In this case, they are a randomized vocal track model, great for a little children's game or something. They'll just chat at each other for ages. You know. They only talk about one thing, which is errors. They go their vocal vowel space is from error to there. You know? This is a Fant model. We've all kind of come across this before, I guess. It's this, you know. You can pick the vowel and drive it with something which models the vocal folds, which is just a impulse with a known spectrum. Okay. So we can take this and make highly adaptable models. So in this case, the lion is actually the same creature as cow. And we can prove that by opening the vocal track model and seeing that there's the driving function for it. And we can kind of move these around to make more lion-like behaviour. Yeah. So make highly reusable models that make a whole bunch of different things. Okay, did we ever look at fire? We never looked at fire. I'm kind of reluctant to go back over this. It's this is an exercise I always do with my students at Edinburgh and at SAE, because it demonstrates the ability to break down a composite sound like fire into its component physical causes. Crackles, hisses and roaring caused by turbulence, explosions and various interactions in the fire. So we end up with having crackles, various kinds of rumbles, hissing, and we combine them together into producing, say, like a plugin like this, where we can have a wood fire. So in this one, you know, we can interact with the object. So if you come up to it in a virtual reality and you throw more fuel on and cause lots of sparks to fly up, then that's kind of what you get. So this is kind of exposed to be a plugin, but obviously this is not how procedural audio is intended to be used. The audio designer uses something like this to parameterize a model which is completely hidden in the game. You know, only kind of exposed by sounds at runtime when you set something on fire. Yeah? So one of the sounds in this is the forced flame model, which is a turbulence effect. I just this. Yeah. Some slightly different variations on that. Now I'm going to combine. I just went back to show you that because I'm going to combine these two together to produce. Okay, let me just break it down. Here's the turbine model, and it's an additive model. It's sparse. Let's bring this down a bit. So these are the components, and that's all of them. Yeah. So you hear how they all shift. We can shift them all together and get the right behaviour. That's in here with a little bit of distortion to spread the spectrum some more. And what I'd like to do is to combine that with a fire model. That's the thrust part of the engine. So let's bring these two together. I apologise to something that's a bit loud. Jet engines are. So, a little backstory to this demo. A friend of mine, Paul Weir, went out on a field recording trip to an airfield with £2,000–4,000 worth of microphones, £2,000 of personal insurance liability for working with a jet engine, and they hired the jet engineer and they had an expert who could operate the jet engine, and they kind of went on the disused airfield and they fired it up and they put mics all around it and they flamed it out and they overdrove it and they got the ignition sound, and basically what we call an analytical recording. They've got everything about this jet engine that you could get ready to layer it into it's one of these kind of F-15 type games where you've got to shoot people down in the plane, you know. So I took those recordings and I analysed them. I used spectral analysis, looking at various amplitude curves and the way the spectrum changed, just fitting the right curves to it. Came up with this model which took the 150 megabytes reduced version of the recordings and turned this into less than 1 kilobyte of code, which produces more or less all of the behaviour of the jet engine quite well. So not just quite well, the players reported, as far as I was able to see from response to what Paul told me from this, that they preferred this. In fact, many times I find that people react to procedural models, they prefer them because it seems like the thing is actually there in front of you, responding somehow in a way that seems realistic. Now, here's the cool thing. If I want to parameterize this model within a real space in the game, I've got me standing next to the jet engine on the airfield hearing it power up. I now take this and I convolve it with the cockpit and I make it so that there's two of these sitting behind me and I'm in the cockpit. Now I've got the pilot's point of view. And I've also got the one where I'm standing on the ground and this thing's moving towards me at 400 miles an hour and it goes zoom. And all of those three sounds are the same piece of code. All that's changed is the viewpoint within the game's engine. So what procedural audio allows us to do is to have a structured way of producing sound in virtual reality. That means we don't have to have 3 sets of sounds, one for the cockpit, one. We get any kind of behaviour depending on where we want to place the listener and various things. So I'm going to kind of try and bring that alive with a more complex example, which is the helicopter. I think we'll jump straight to that. Okay. I think I'll make this the final one as well. So the helicopter, very interesting, complex mechanical device. It's got an engine, usually a gas turbine these days, but this kind of models a cylinder engine, a main rotor, a tail rotor, and what's interesting is that there is a complex interrelationship between these parts. They don't just exist separately. So if I want to take the lift off, if I want to move forward, I have to tilt the vehicle this way. So the lift produces some vector of the force moving this way now, so it pulls the helicopter forward. But if I increase the angular velocity, the angular acceleration of the rotors too quick, it has a torque effect on the whole vehicle, tries to spin me round. So I need to increase my tail rotor speed. Yeah? Now what couples these together is a clutch and gearing system, which you can hear that little whining sound there. So what we're starting to see is that the kind of behaviour that, say, we saw with the original motor, where there's a macro level behaviour, we can now have a macro level behaviour involving multiple parts interacting. So let's just kind of break down the original sound sources. We've got here's the gears. Here's our very poor little engine, but it's just, there's some jitter there for, you know, and there's some parabolic pulses which kind of model a petrol engine, and a very cheap waveguide. Yeah? Notice that we can couple that to the tail, but they're independent. Yet if we move the engine speed, you can hear an interrelationship between those two parts. Yeah. Normally we only want a very, very small bit of the gear mix, just hiding there, just poking out of the mix. Yeah. And here's what most people associate with the helicopter sound, is our main rotor sound. There's actually like a whole lot of very interesting things to say about the helicopter. As it comes overhead, you'll have asymmetry. This one is moving towards you, this one's receding. As it passes overhead, it'll flip. Yeah. The sound is highly directional. It's produced by something called blade slap, where turbulence from the fore rotor hits the following rotor and causes it to jolt, so it excites it a particular position on the rotor, which is supported in the centre. This causes these spokes of sound to come out very directionally, so if a vehicle's not converging on your position, what you'll hear as it passes obliquely tangentially is but if it's coming right at you, you'll hear like this particular constant pattern of blade slaps. So one of the ways we use to know whether it's constantly converging on your position. Another thing is that you'll hear a different kind of behaviour with the tail rotor during certain manoeuvres and so on. So what we can do is we can take the player data that the pilot's using to control the vehicle in virtual reality and make a behaviourally realistic model. Now, this, going back to one of the earlier comments about realism, this is where the rubber hits the road with this discussion, because realism is not about fidelity. Realism is about behaviour, and whether or not, as David Beck in C-Sound, Richard Boulanger's C-Sound book, calls it acoustic viability, and I haven't really heard it called anything better. I think that's a great term. Is how well do the physical parameters map to what we perceive as the audio signal, And if those make physical sense to us, we intuitively say, that sounds right, that sounds plausible. Whereas if you just kind of throw models together randomly without a coherence, they don't. So what I'm going to do is I'm going to assemble the parts of the helicopter. The helicopter has a ground effect too, so here's the vehicle and here's you on the ground. There's a direct path and there's a ground path which reflects up. And this is the same for any airborne vehicle. As it moves, you'll hear a notch filter sweep down and up as it passes overhead. So let's kind of bring it up and then send it off. So this is the kind of distancing function that we might use in the game engine. It's not modelling a dispersive effect, but it's large distances, you know. And then we'll bring the vehicle back close to us again. And you should hear how the various parts kind of come out of the model. That's the whole show. That's most of the material that I've got to demo. There's some other bits, but I think it's more well past time that I kind of hand it over to you guys. So thanks for your patience listening to me with this tonight. Thank you. Okay.
So the people just have to speak up.
Yeah, and I will repeat the question for the benefit of the recording. Are we still doing one?
That's fine, yes.
Okay.
Would you, yeah. Otherwise people will have to shout.
Yeah.
Which isn't the problem. If you fancy shouting, please shout. Thank you, Andy.
A question. How much of this process is creative, and how much? I mean, when you do a model, are there several ways you could make that model which would sound roughly the same, which would have different physical paths, for example? I'm just wondering whether when you do a model and you get it right, are you actually? Do you think is reality going to be like that? I mean, is it sort of a one-to-one mapping, do you think?
Yeah, definitely not. So the question is, to what extent is is it an aesthetic component versus a strictly formal? Is that a good reading of it? There's a mixture of both. The technical informs the aesthetic, but ultimately we're producing things for arts and entertainments. I like to underscore that with saying that there's a point of going too far with physical modelling, which really misses the point, because what we're after is the perceptual effect at the end of the day, and often the visceral emotional effect. So we're looking for particular features of a sound. When you look at how, say, Merck did helicopters in Apocalypse Now, there's no helicopters there. There's just somebody swinging a chain, which sounds very menacing and frightening. So, I mean, most sound designers, we know the sound designers amongst us, most sound design is smoke and mirrors. It's trickery. It's producing the right effect in people. There's a temptation to level criticism at a procedural approach of being over formal. And I kind of reject that. I think what it is, it's just pushing the whole scene forward. But that depends how creative you can be in producing these sound models, and how you can then use them creatively in a film or game. Depends partly on your technical knowledge of the model, and partly on your ability to just have a good ear and hear when it's right and tweak it around. And there's a lot of that. In fact, lots of my models are kind of justified ex post facto. I messed around with them and I made them sound great, and then I went back and kind of worked out why it sounded great. And it's, now I look at the physics literature and see, that's why. So, and some of them are done absolutely rationally, stepwise, and I'm very surprised at the end that what I end up with sounds just like it should. So I think that's evidence of possibly evidence of good research, because it goes backwards and forwards both ways. You can kind of tread from a top-down aesthetic viewpoint and end up with what you want. Definitely a mixture. And there's it's as almost as a maxim of programming, which is one of the mottos of the Perl community, but it applies to all programming. There's always more than one way to do it. There's almost an infinite mapping of processes onto a result.
Do you find that when you've been working on one particular sound for a very long time, it's kind of like repeating the same word over and over again? So when I did mathematics and did logarithms and things, log started looking like a fake word.
Yeah.
Do you find that you have to go back and hear the real thing again because you get diminishing returns on what you think it should sound like?
Okay. When working on a sound, does one become desensitized to that sound and need to kind of refresh with reality? Yes, definitely, and I think that's a psychological facet of any creative pursuit. You get the same sort of singing or playing an instrument or something, but there's an interesting mechanism in effect in designing a sound when you're working with. It's like composing a piece of music. Is you have mentally an internal model of the target, and you have the thing as it exists in reality, and then you try to appreciate the difference between them, and then you're trying to move them together. And what you hope to do is to move the thing you've got closer to the thing you want. But what happens with fatigue in this iterative artistic process is that you're in danger of moving the thing you want closer to the thing you've got, and settling for less. And a nice cup of tea and a 10-minute break makes all the difference. Yeah, that's an artist's answer. The technical answer is probably neurobiology or something. I don't know. Yeah.
So do you visualize a future where, as well as computer game audio, this will replace conventional sound effect CDs and libraries, where instead of buying a CD, one would buy an algorithm?
In terms of as a product?
Yes.
Maybe. I think there's possibly a market for procedural designs. I don't know. I think that the real market is for the skill of the person who uses the procedural model, not necessarily the creator of the procedural model. So there's a fairly limited market for making these things, and once you've got a toolkit of basic components, then it's down to the artist. But I think the straightforward answer is no. I think there's always going to be a place for sound effects, for recording. I mean, this is absolutely to supplement recording. I don't think we're ever going to see, like, the idea. It's not an ideal. An idea of a fully computational audio piece of media, either be it film or game, is a landmark that will be really cool, and we'll know that we've arrived when we get that. But if you look at, say, CGI now, most of the CGI is informed by mocap from real actors. So there's now like a return of recorded reality, but the reality is being captured in a different form and put onto a modelled thing. So I think there's a continuum between procedural methods and recording methods, and what we're seeing now actually is the way that it's being introduced in some games is through different forms of granular synthesis based on what we call grain dictionaries. Bob Sturm's done a lot of work on this, and there's a lot of other people who've done work on advanced granular microsound methods where you can analyze real sounds, steal from the palette of them, and arrange them in a way that allows you to model them in a more procedural way. So there's sort of continuum between them. What does that mean for products? Okay, I'm going to come out and say something quite controversial here. I think that it's become a bad thing that sound is commodified, in that it becomes a recording, becomes something that you take and curate and own and move around. That's led to a sort of stultification. I think bringing interactivity and dynamics back into the mix through something like this maybe will reinvigorate a lot of interactive sound design. I don't think it'll ever replace it. I can't see because of the light, but I can see a wave. So yeah.
You're saying towards the start of the talk about research into the psyche of the user.
Yeah.
So doing canned samples versus procedural audio.
Yeah.
I might have missed something when you said it. I mean, much research been done, and if not, do you think that research is necessary to help push procedural audio into the attention of the games manufacturers? And also, how would be a good way to do it? Would it be just an empirical case study, just get some guys playing some games with canned samples, see what they think, and some guys playing some games with procedural audio and say, what experience did you prefer?
Yeah, okay, so user studies, formal studies on the efficacy of procedural audio to perhaps convince the games industry to adopt it. Okay, from an academic point of view, yes. I think it would be really good. It's a great research opportunity to look at synthesis again, to look at how close we are in various ways to producing sound effects ex nihilo, which satisfy the requirements emotionally and so on for media work. Convincing the games industry with that method, no, they won't. They don't care. They won't pay attention to that. It's such a practical pursuit making games. You've got to ship titles, and actually, Gordon Doherty's a very interesting person to. He's vocal and very smart about the real politic of how this works in the games industry. A study that said, "Hey, this is just as good as sampled audio," I think would kind of be a no shit Sherlock study. We know that we can make very good synthetic audio. The questions around the production method, the tool change, the workflow, and so on, I think that those are the things that would convince uptake in the games industry. But from an academic point of view, I think it would be very interesting to see if this stuff flies. Yeah. Yes. Shall I take the one over there? I'll apologise. I'll come back.
You said a lot about the principles behind the procedural audio and how you construct the models from the various elements.
Yes.
What you didn't say much about is the implementation side of it. I mean, you've got a very interesting tool there.
Yes.
Something about that. Is that something that's your proprietary thing, or is it a commercial thing?
No. Okay. Thank you. That's a great question. With regards to the implementation layer and the software that I'm using here. For those that don't recognise it, I'm using Pure Data, which is written by Miller Paquette. It's a visual data flow language, which is particularly powerful and appropriate for DSP. And one of the reasons that I love it, even though I'm versed in many other kinds of implementation, is it's my teaching tool of choice. I think it's one of the data flow in many ways is a massively underrated pedagogical tool. Its educational implications are huge. People immediately kind of plug into, literally, it's like, hey, here's a box and a wire and so on. So what I discovered about data flow is it greatly accelerates the production process. What would have taken me a week to kind of produce in C++ and then debug, I can do in a night. I can do now in an hour. I can literally put together. So people, and those of you that use PD will know you become very fluent at plugging these boxes together, and you can kind of produce ideas in hours, not weeks. It's open source. It's of a family of data flow languages, of which Max MSP is another one by the same author. There are many kind of ways out of it. There's now a libpd, which is you can just hash include libpd in code and use this tool to export a net list, which can then be drive a runtime engine within the libpd library. So it's highly embeddable, and in fact a company producing reactive music called RJDJ and several other companies have kind of emerged on the back of this quite revolutionary tool, really. And it's very compact. I think it's only a couple of 100 kilobytes in the we call it the Miller Vanilla native version, which is not many so not many unit generators. You could compare it to C Sound and Super Collider. That they're just different languages, and I find that this is very speedy way to develop, and I find that it lowers the bar to entry for non-programmers and non-DSP specialists. So even if you don't know what convolution is, or you don't know how to do a table lookup, or you can start plugging things together and getting results very quickly, and then fill in the theoretical and academic knowledge afterwards. I could talk about pure data all day, by the way, but I'm going to try not to, because I love it.
Can we have the last question?
Yeah.
What do you think about timescale when it comes to generating assets? So if you're working on a game,
Yeah.
and we've got an integrated procedural system,
Yeah.
something like that, then because I really like the idea, and I think that the sound that you get out of a procedural system is a lot more responsive. It makes you feel more engaged with what you're doing, and the
Yeah.
interactivity is there. But at the same time, if you've got to do a menagerie of animals,
Yeah. How do you do that quickly? Okay, so how do we manage that this is a very time-consuming process, or apparently a very time-consuming process in a real project? A couple of things to say about it. It's a snowball effect. If your team have expertise in procedural audio, you've got these reusable components you can start plugging. You're not building from the ground up each time. So by the second project or the third project, you've always got a huge library of stuff that you've tried out in earlier projects that you can pull in and modify and build on. So the development time goes up. And the development time goes up as you gain confidence and expertise at it. What's different is that if we would try and tap into the skill set of an existing audio guys, there's lots and lots of that expertise already out there. So there's so many. Everyone can use Pro Tools. Everybody knows how to compose in Logic. Everyone knows how to handle a microphone and do the traditional way that we've done it. So I can kind of pick 10 guys and make an audio team and trust that they'll know what they're doing and they'll produce assets very quickly. If I go down the procedural route, I think even with 5-6 years of teaching this, there's many ex-students out there who are doing amazing things. There's still not it's not like a widespread skill base of people versed in. There's a few startup companies who you could go to and say, could you produce us some procedural assets? And they've got that expertise. But it's not as widespread that if I was to, HR wouldn't be able, they'd put an advert in and they'd probably get like 1 or 2 people turn up who fancied their chance at coding new procedural assets. And they'd take a real long time to do it to begin with. But it's like all things. Once you've invested in it, and it's a chicken and egg situation, to get a new technology going, you have to invest in those people and training them with a view to like a long future of working in this way, and make the commercial judgment. Does this bring value to my customers in some way that can justify the investment in the technology? Because the technology is not just bits and bytes, it's training, it's culture, it's expertise that's out there, and so on. So it's tough, but I'm imagining that when in the Tron days, when CGI was in its early days, those 10 or 20 guys in Hollywood who could do CGI stuff were hot property, and they made a lot of money once the thing started to move. So maybe by doing something like that as a startup or a casual game producer, you're really making your mark. You're doing something which is not typical out there, and we're seeing that. There are examples, and it's finding and training the right people, and I hope that answers the question.
Thank you very much, Andy.
Okay, thanks, Ben. Thank you everyone for hearing me.